So I'm going to be doing a few more sums before further explaining the concepts of integration and diving deeper into this topic. This is the first sum for today. Tan inverse root over 1 minus sin x divided by 1 plus sin x. The root is over the entire numerator and the denominator in this section. Now how do we solve this sum? Just for your information, you can just pause this video if you want to solve this sum on your own, or solve it with me, however you like it. How do we solve this sum now? 1 minus sin x divided by 1 plus sin x. And there's a tan inverse over here. Now remember, this sum is to be solved with the help of the concepts which I have already taught you. 1 minus sin x divided by 1 plus sin x. We know that sin 2x is equal to 2 sin x cos x, and the same stands for any value of this 2x. We can write it as sin x is equal to 2, and then over here we have to write x divided by 2, since it's 2x divided by 2, which comes to be x in the first case. In the case which we require, it becomes sin x by 2 multiplied by cos x by 2. This is what we have. So how do we implement this over here? We also know that 1 is sin square x plus cos square x. We can substitute any value in place of the x in this case. That's also possible. And since we have x by 2 and cos x, sin x by 2 and cos x by 2, so we can write cos square x by 2 plus sin square x by 2 in place of 1. This is what we get from simplifying this trigonometrical function under the root is cos x by 2 minus sin x by 2 whole square divided by cos x by 2 plus sin x by 2 whole square. Now since there is a square in the numerator and the denominator, and the root is over the entire expression, we can remove the square and the root together. Basic mathematics. So we have left is we remove the root and the squares, and this is what we get: cos x by 2 minus sin x by 2 divided by cos x by 2 plus sin x by 2. Now there is seemingly no way to remove the tan inverse. How do we remove the tan inverse? We have to create a function within the brackets which has just tan at its head and other required functions defined within tan. So what are we going to do now? We are going to divide the numerator and the denominator with cos x by 2, and that will do the trick. What happens when we do this? Let's see, shall we? So this is what we're going to do. We're going to divide the numerator and the denominator with cos x by 2. So what we are going to have is tan inverse 1 minus tan x by 2 divided by 1 plus tan x by 2. You might be familiar with this form of tan. It's the tan subtraction method. When we demonstrate, when we subtract two variables within tan, this is the basic expression that we get. We have tan A minus tan B divided by 1 minus tan A multiplied by tan B. But there seems to be no tan in the first monomial over here. So what do? We know that 1 is equal to tan pi by 4. So we can just replace 1 with that. And in the denominator, the tan x by 2 can be said to be multiplied with 1. So we just have the general expression in our case. And we can simply replace it with what we found on simplifying this expression. This is what we have. Now since we have a tan inverse and a tan, both of them negate each other. And what we're left with is pi by 4 minus x by 2. And we're back to the first principle of integration. So our answer will be, we can integrate this simply in our mind. It doesn't matter, there is nothing really to show in the integration part. The main part was the simplification of the function to get what we needed. So this is the answer that you should be getting, or you might have got about solving along with me. This is the first sum. This is the second sum, which we're going to do. You can again pause the video if you would like to solve this on your own, and then math solutions with me. At first glance, this seems to be quite easy. You can just substitute cos x and you get sin x dx. So you can get rid of the numerator and be left with 1 minus z or t or a or whatever, multiplied by 2 minus the variable you've taken. But how would you solve the denominator function then? That would become quite difficult. So I have another approach to this sum. What I'm going to do is, I'm going to take 1 minus cos x as a variable. Let's say z. And when I differentiate both sides, I get sin x dx, since the differentiation of 1 is 0, and minus cos x. So we get sin x dx is equal to dz. So we just replace sin x dx with dz. dz comes in here, and we have z over here. We have to derive 2 minus cos x. We have 1 minus cos x. So 2 minus cos x is nothing but 1 plus 1 minus cos x, which is 2 minus cos x. And this can be written as 1 plus z. So we just replace it with 1 plus z. And this is what we get, z plus z square, the denominator. Now, how are we going to solve this? In fact, it would be better if we just leave the denominator be like it is, because the method I'm going to use doesn't require any of those. We just let it remain in the predefined form. The numerator has 1. We can add z to the numerator, which would make it this balance. So we can just subtract a z. It doesn't really matter, it's the same. 1 plus z minus z is 1. So it's the same as this. But this is a lot easier. This is an easier method to get closer to the answer faster. So what do we do now? We split from the minus. The left of the minuses becomes one expression, and to the right of the minus we get another expression. So what we have is 1 plus z divided by z into 1 plus z minus z divided by z into 1 plus z. Now you might be understanding where this is headed to. This 1 plus z in the numerator and the denominator, they are identical expressions, so they cancel out each other, and this z and z, they cancel out each other as well. So what I'm left with is 1 by z minus 1 by 1 plus z. Exactly. We're back to the inverse integration. Now, did I have to mention that the inverse integration works only on the first, it has a condition to work. It works only if the denominator has a degree 1. Doesn't matter if it is added to some number or multiplied with some number, divided by some number, doesn't matter. It always has to have a power of 1 though. And that's true in both of these cases, so we just have the answer in front of us. It's log mod z minus log mod 1 plus z plus c. Now we substitute back the values of z and 1 plus z. Z and 1 plus z. What we get is the answer right in our hands. 1 plus cos x minus log of 2, sorry, this will be minus, sorry about that, 2 minus cos x plus c. Now since we have a negative between the log, we can write it like this, say logarithmic, it's a logarithmic rule, we can write it like this. So this is the final answer that we get from this sum. You can view the solution longer by pausing the video. I'm going to go to the next sum now. This is the last and final sum of today. The third and the final sum. At first glance, if you can get what I'm going to do in this sum, it's really good. You can pause the video again if you want to try this on your own. I suggest you do that and try to do it on your own for once. Just try it, it's quite simple. So let's begin solving. As we know, sine 2x can be written as 2 sine x cos x. Now since there's a 2 in the numerator and the denominator, they cancel out each other, and we are left with a root tan x divided by sine x multiplied with cos x. This is what we're left with. What are we going to do now? How do we solve this sum? How do we get to solving this sum? In most cases, when we have a tan, what we should try to do is get a sec square in the same function, in the same integral, so that we can substitute and make our way out of the problem. And that's exactly what we're going to do in this sum as well. First of all, we have a cos x. Now we can write this as sin x divided by sec x. Since cos x is 1 by sec x, we can write it like this, which then comes to be root tan x multiplied with sec x. Divided by sin x. We're getting closer, you can feel it, right? So, you saw what I did, I just brought the sec x to the numerator. What are we going to do now? We're kind of, we just have a sec x. The sec x does not help because we have a root tan x. So, if you have already thought of this, it's pretty good. You need to divide the numerator and the denominator with cos x. You can just write it as multiplying with cos x. So this cos x goes to this denominator, and this cos x goes to this denominator. So when this sin x is divided by the cos x, we have a tan x in the denominator, and we have a root tan x in the numerator as well. When a sec x is divided by a cos x, 1 by cos x is sec x, so this becomes a sec square x, just the expression we were trying to make from the expressions we already had. So what do we do now? The root tan x, so this is basically root tan x multiplied by root tan x. So we have a root tan x left in the denominator. is sec square x divided by root tan x. That's what we're left with. Now obviously you might have guessed, we're going to substitute. Since tan is beneath the root, we can substitute it with the square of a variable for convenient purposes. When we have say z, we get z outside, we can just replace it with root tan x again. For convenience, we are taking z squared, tan x to be z squared, so that we get rid of the root sign while integrating. So when we differentiate both these sides, we get 2z dz. This sec square x is replaced with 2z. 2z. 2z dz divided by z squared, which is equal to 2z divided by z dz, which is again equal to 2dz. 2dz, that's kind of a fun. So the answer is c plus c, 2z plus c, because we have 2 multiplied in the final answer. We substitute back the value of z. Now so z is equal to root tan x, since tan x is equal to z squared, z is equal to root tan x, and that's what we're left with over here, 2 root tan x plus c. So that's it for this video. In the next video I'll teach you a few more concepts of integration, and thanks for watching.